introduce our internal speaker this week. So it's a great pleasure to have Professor Jiazi Chen, who is an associate professor in our department. She received her PhD from Princeton University. Before that, she got her bachelor from Columbia. And her research is majorly focusing on multimedia systems and augmented virtual reality. Uh, and she received a couple of awards, including the NSF Korea Meta Faculty Award and Adobe Data Science Award. And today she will be talking about something interesting about mixed reality security and streaming at the system and application levels. With that, the group is yours. Thank you.
Thanks a lot. Hey, everyone. So thank you so much for being here. I know people have various deadlines and so on, so appreciate your time. So as Ching mentioned, I'm working on multimedia systems. Just a little backstory. So my background is in computer networking and wireless communications, but this talk is about mixed reality and kind of security aspects. So just to tell a little story how I got there, worked on different kinds of video streaming and multimedia systems during my PhD, got really interested in mixed reality when I started my faculty job, and then started collaborating with people in cybersecurity, and that's how I arrived at this topic today. So let's get started. So multimedia is central to our interconnected digital lives. So I don't know if you guys watch Game of Thrones, very popular. I love Game of Thrones. So that's when Netflix moved from their DVD and they started having online on-demand video, right? Which is ubiquitous today, but it was not that long ago, 2007. During the pandemic, we had endless Zoom meetings, as you know, right? So multimedia and real-time multimedia was very important to our lives. And as time goes on, Facebook changed its name to Meta, so illustrating this interest in the metaverse, whatever that is. So new forms of multimedia are continuously emerging. The question is, can we keep up with these efficient delivery? Let me give some background about mixed reality. So what is the continuum here? On one end, we have a classroom, just like where we are today. And the other end, we have purely virtual worlds. This is a screenshot of people playing Second Life in VR. On the middle, we might have augmented reality, which is where most of the world is real, and there's some virtual content on the sides. We also have augmented virtuality, where most of the content is virtual, and there's some real-world things here, which is the user's hands with their keyboard. So there are exciting mixed reality applications that are supported by major players. Cool applications, there are defense and military applications, applications for education. This is an app that my students developed as part of my VR class that I used to teach, where they use VR to help teach rotations in VR. And also things like public safety for firefighting and for those applications. And then underneath these applications, we were supported by various types of extended and mixed reality platforms. So things like Unity, HoloLens has a lot of SDK support, Google Play services for AR or Android XR, Apple ARKit, so many of these underlying platforms. And then underneath that, we have onboard sensors that are on the device that provide inputs to the mixed reality platforms and from there to the applications. So we have a ton of sensors on mixed reality devices, things like eye trackers, inertial measurements units, various types of cameras and microphones. And we also have infrastructure sensors like wireless base stations that help our devices communicate with each other. So the reason I'm showing you this stack is to show that my work is mainly on maybe this layer or below. So I'm not specifically I do work a little bit on applications and use cases, but mostly I work on the mixed reality platform and below, which support the types of applications that we want to build on top. Okay, so that was a little bit of background about sort of multimedia and mixed reality. So let me tell you more about how I see this, sort of the outline of the talk. So how we can see this is that we have real world users, and they are also existing in some kind of virtual world. So there's the real world and the virtual world, and they can be a little bit different. So here's my real users. They're wearing headsets, and they may have some virtual representation where they're seeing some virtual content like this Pikachu or like this sign. So how do we mediate between the real world and the virtual world? So going from the sensors to the virtual world, going from the headset to the virtual world relies on the devices using sensors. So the headset's sensors detect things about what's happening in the real world, and use that to generate virtual content. Where is that virtual content stored? It's stored in some kind of, we can think of it as a database or a piece of software, which we're calling shared virtual world state, that keeps track of all the virtual things that are in the world. So it keeps track of the Pikachu, it keeps track of the underground gas line sign, and so on. And then how do we get back from the virtual world back to the real world? Well, the interface between that is human senses. So humans are going to perceive what's happening in this virtual world and then react accordingly. So all I'm trying to say here is the way I see things is we have the real world, we have the virtual world, and different types of sensors are mediating between the real and the virtual worlds. Headset sensors on one side and human sensors on the other side. So what am I talking about in this talk? Well, we have these interactions between the real and the virtual worlds, and this creates opportunities and also weaknesses for us as researchers. So in this talk, I'll focus on weaknesses that come from these headset sensors. So if I can spy on things from these headset sensors, I can try to understand some user behaviors or environmental behaviors and basically try to figure out some private information. I can also spy on, or I can also manipulate what's happening in this shared world state that keeps track of all the things that are happening in the virtual world. So if I can manipulate this shared state, I might be able to cause some bad effects downstream on the mixed reality application. And finally, the third part of my talk will be about opportunities. So can we understand how users behave in response to mixed reality content and exploit this kind of behavior to improve system efficiency? So that's the outline of this talk. Real and virtual worlds, mediation between them by senses, either on the headset or the sensors, and that creates opportunities and also weaknesses in the security domain. Okay, so with that, then I'll get into the, I guess, meat of the talk. So I'll show you two particular pieces of work that I've merged together. So these are system attacks at the system layer from malicious applications. So let me provide some background. So usually when you're wearing a headset, you have sensors on them, IMUs that are doing 6 degrees of freedom, tracking of the user's head. So that could be like position, XYZ coordinates, and also rotation in terms of yaw, pitch, and roll. And these are sensed by the headset's gyroscope, accelerometer, and also from the cameras. So what is the main idea? So let me preview an example of the attack. So this is a user. This is actually Carter, one of my graduated PhD students. And he is typing something in VR. So he's typing something. And what we can see is as he's typing using his hands and the controllers, restart the video, he's also very subtly moving his head. So the main idea of this attack is it possible to spy on what the user's head movements are and use that to infer the typed words from the user's head movements? Why do we want to do that? Well, maybe if a malicious app can do that, they can try to understand what the user's typing, maybe leak sensitive passwords, confidential documents that they're typing in the virtual world.
How do you type in a virtual world?
So there are different ways of typing. In this one, he's just moving his hands and moving his hands and like clicking on a keyboard.
Oh,
So he's pressing buttons. There are other ways as well where you just use your hands directly and you just like poke a virtual keyboard. We didn't study that type specifically, but people have done that in the past. By the way, yeah, like feel free to interrupt or whatever. It's always more fun that way, right? Than just me talking at you for an hour. So what's the threat model? So our threat model is that here's my device. On it are a bunch of sensors. There's some SDKs, and there's some applications that live on top. So our threat model is that just like on your phone, right? You can go to an app store and download a bunch of apps. You can do the same thing on these devices. You can go to the, let's say, HoloLens store and download some applications. So our threat model is that you've downloaded an application and it's either malware or has some bad libraries inside that are malicious, and they can possibly spy on the other applications that you have running. So we assume that this spy application has standard application level permissions. We don't assume any physical access to the device, and we assume the application has just normal permissions to probe certain performance counters or sensors data that are freely available. So here's the device architecture. So we have some hardware underneath that lives there. And we also have something called rendering performance counters, which we're going to use in this work. And what these performance counters are stuff that you can extract from the SDKs. And they're just basically debug information. So they'll tell you like how much memory your application is using or how much CPU, what the CPU frame rate. So these are freely available to applications, and they're basically used by applications to help them debug their performance. And we also exploit sensors. So sensors here are just the standard ones I mentioned, like cameras, IMUs, microphones, and so on. So what are these leakage vectors we look at? We have memory allocation APIs, rendering performance counters that are provided by standard game engines like Unity and Unreal. So things like the frame rate, GPU, CPU frame rate, refresh rate, and so on. Thread counters that is telling you how long threads are running for. Render task counters, so these are like graphics specific, so how many draw calls you're making, how many primitives, like number of triangles that are displayed on a screen, how many vertices are being drawn, and things like that. And we also rely on sensor data, like I showed you in that little clip earlier, like head acceleration or the velocity. So these are the kinds of leakage vectors we exploit. And we're able to show 3 different types of attacks. So one is spying on user interactions, just like the keyboard one I was just telling you about. So that's just basically typing on a keyboard, as well as other types. We also spy on what other applications you have open. And we also spy on the real world environment. So here's the spy application. They are looking at certain leakage vectors and trying to infer information from the headset about, in this case, the environment, like what bystanders are present. So the setup we use is we use 2 popular headsets, an AR headset, which is the HoloLens 2, and a VR headset, at the time Quest 2. We collected data from a number of volunteers. It was 20 volunteers in the end. First time when we submitted the paper, we only had 10 volunteers. Then they're like, revise, add more volunteers. So we ended up with 20. It's a pain in the butt. And they had various diverse characteristics. So the way the attack generally works is that we take this side channel signal from the performance counters. We do some feature engineering on it. We run it through a machine learning pipeline, do some classification regression, and then try to infer whatever behavior it is we want. All right, so that's a standard pipeline. But the main thing is actually showing that you can do this with the standard application level permissions of a regular XR app. So what are the types of things we demonstrated? One is the typing one that I showed you. So the specific example for this one is the key point is that most popular VR program app environments like Unity, which is a standard game engine that people use to make VR applications, they provide all the apps that are running on there with real-time head pose. And why do they do that? It's because every application needs the head pose in order to continuously update this display. So if you turn your head, I need to know the head pose so I can update what's being displayed. So it's something you can't really get rid of. So in this, this is the experimental setup. So we have a malicious background app, in this case, which is what we call the chat window, number 1 here. Oh, I'm sorry, no, these numbers don't correspond to this. This is the background app. There's for example, a Beat Saber, and it's recording the head pose. The user types sensitive data into the foreground application. Here it's a chatting application. The background app would then infer whatever the user's typing in the foreground, and then profit, right? So yeah, I just want to emphasize over and over that no special permissions are needed by the attacker. The background application always has access to the head pose to do this kind of inference attack. So the main question is, the pipeline is pretty simple, right? Take some data, throw into machine learning model, like ta-da. So the question is, does it work? So the way this whole project started, right, the reason we spent all this effort on it was we did a couple of examples first of all, to see any intuition of if this would work. So here's a couple of time series traces. So the x-axis is time or frame, and the y-axis is the orientation speed, like the angular speed or the linear acceleration on the y-axis. And this is the user typing the word lazy. And these are the traces from that. So this is one set of traces from user typing the word lazy. This is a second set of traces from the user typing the word lazy. So what we see is that, well, what we did initially for the study is we looked at these traces and we kind of eyeballed it. And we said, is there any similarity between the users typing this word over and over? And you can kind of eyeball it, right? You see the red is here, it's kind of similar to the red here. Right? So that means, okay, this might actually work if there's some repeatable patterns that we can see in the data. Right? Before we shove it through all that machine learning pipeline, we need to see if it actually, can our human eyes even see this? So this is promising. And here's a user typing another word where they type the word quick. So another observation we have is that when a user types the word lazy versus the word quick, we see it's different. Right? So that's also going to give us some intuition. So once we saw these results, we were happy. We're like, okay, this might actually work. And then, then we started collecting a lot of data, feeding it through the pipeline and so on. But this is like the core thing that once I saw it, I showed my grad student, and we're like, yeah, this is going to work. And we spend all the time to flesh it all out for a full paper. Okay. So just a little more detail on the technical side. So here's some traces that we have. We have a more complex problem because if you want to do the typing, we want to both figure out like individual words, and user might be typing a full sentence. So we want to both figure out where the words are, like segment the sentence into different words, and then also infer for each word what it is. We also segment to words. We also segment to character pairs. So here's our original trace. We might segment into longer pieces like words, shorter pieces like character pairs. We have two different like classifiers that we developed, a word classifier and a character pair classifier, and to try to infer words or character pairs. Right, so if the original sentence was, the quick brown fox jumped over the lazy dog. So the idea would be, can we infer the words the and quick or the character pairs? So you might ask why we want to infer character pairs, right? So the idea is like if people are doing passwords entry or something, then that's going to be random characters. So we want to be able to infer on a shorter time scale. So let me show you a little bit about the sentence segmenter. This is here. And the main idea here is on the x-axis here is time, and the y-axis is the probability of typing a spacebar and the user's angular acceleration or angular velocity of their head. So the main idea is to segment a sentence into words. You just try to figure out when they're typing a spacebar. And you can imagine the intuition, like maybe they're looking up at the keyboard and they look down a little bit to look at the spacebar. So what we see here is the black lines are the ground truth of when you're typing a spacebar. The blue line is the user's like head movements, and the red is some prediction probability that we did. And what you can see is the red lines match up fairly well with the spikes in the red line match up pretty well with this vertical ground truth black lines. Okay, so in the interest of time, I think I'll speed through these results. I want to show you other types of attacks, right? I hope you believe me that it worked well. So I want to show you other types of attacks. This one is a bystander ranging attack. So the idea here is that when the user steps into the field of view of the device, can we turn this device into like a secret spy camera, kind of? So what we do here in this application is we have the spy app. They're looking at that set of leakage vectors and trying to profile these leakage vectors and infer whether there's a user in the view. So the main reason this can work is because under the hood, the headset is constantly trying to build a 3D model of the environment. So this is a spatial mesh that shows what the environment looks like, and the headset is constantly doing this kind of processing. So the key idea is that if a bystander steps into view, this spatial mesh will change a little bit. And that will cause something to happen to the device will do more processing, or something will happen to the performance counters that then lets you infer whether a bystander came into view. So that's the main idea. Then here's just some data about it. So the particular performance counter we looked at was the CPU frame rate. So the x-axis here is time, and the y-axis is a plot of the CPU frame rate we measured. And the arrows here show when a person stepped into view. So here, at this point, a bystander stepped into view, the CPU frame rate dropped, presumably because the device started doing more processing to detect the person. And when the bystander left, there's also a deep spike. And then this plot is for a person that is 0.5 meters away. This plot is for a person that's 2 meters away. And this plot is a plot for a person that's 4 meters away. So the main thing is that you can see these trends. And when we repeat these experiments over and over, we are able to see these trends consistently. So again, that's the motivation. And then we do a whole bunch of things, machine learning, data preprocessing, et cetera, to like formalize this. But this is the main intuition. So here's some results. Our main thing is try to infer the bystander distance at various distances. And we tried various types of machine learning methods, nearest neighbors, decision trees, random forests, boosting, some kind of majority voting. Doesn't really matter. The main point was which one did the best for us, right? So here was the decision trees. The mean error was 10.3 centimeters in trying to infer how far the bystander was. Okay, so hopefully that gives you an idea. And so in that collection of in those two papers, we actually inferred many types of user behaviors or environment behaviors. Typing I showed you, bystander distance I showed you, and other ones I didn't tell you about today, but like they were things like what other applications are running, what kind of hand gestures users are making, what kind of voice commands the user is doing, and things like that. We tried many leakage sources. So some of them used performance counters as the leakage source. Some of them used motion sensors. And then we had various success rates on various devices, which were decent, I would say. But yeah, in line with other types of these other types of performance counter-based privacy attacks. So we also tried some simple mitigations, right? How do we defend against these attacks? So one idea you could have is to take the data that's being leaked and try to reduce the precision of it, right? So maybe the device is only going to report performance counters at a lower, with fewer significant digits. So here the x-axis is number of digits, the y-axis is the accuracy, and we can see that even as we reduce the number of significant digits, it actually didn't work that well, this defense, because the lines stayed horizontal. And we also investigated like what happens if the device reports the performance counters less frequently, right? It doesn't give us fine-grained information. And again, we saw like, okay, if we reduce the frame rate a lot to like, I think this is a log scale, so probably like 2 frames per second, then the attack didn't work very well, but it still worked pretty well. So we left this kind of as an open question, like these simple mitigations were not very effective, and we think more work is needed. Yeah.
For an awful lot of exposed performance counters and general purpose architectures that people used in attacks, and then they shut a lot of them down. You had to be root to access them, that sort of thing. But it looks like this one's more fundamental, because even if they didn't share the frame rate with you, you could have your application ask for something to be done and then look at wall clock time for those 2 samples to see how long it took to complete. So even if all you have the ability to do is have your application make code run wall clock time, you could still get information about frame rate, I think.
The wall clock time of like
On the system. What is the current time of day right now? Now go do this thing that's computationally intensive. Now what's the time of day again? And even if it didn't have an API to give you frame rate, you can still use that to see how heavily loaded the processing.
Yeah, I see what you mean. Yeah.
Like this is a hard one to work around by changing the API, because you can't take away time of day.
Yeah, I guess that could be another. We didn't explore that one specifically, but
I was thinking, like, what if you just shut this down totally by
right, yeah.
not even providing
Yeah.
API to get frame rate? Doesn't fix it.
Yeah, well, it depends, because some so first of all, I think we do always disclose these things, and other researchers also disclose, and sometimes some of the APIs do get shut down. But I'm not sure about that one because sometimes because the thing you're saying with the wall clock time doesn't give a lot of information. Like
Yeah.
it's a more high level, right? It's like a more high level performance counter. But one thing we are actually playing with on the wall clock time thing is like contention based attacks. So if I can like trigger a function that's causing that's doing a lot of processing stuff, right? And then increasing the time, and then try to see how that impacts like other applications in a bad way. So not exactly what you said, but just related to the wall clock time.
Could follow up with a slightly related, if you reduce the float precision for like the rotation angles, then presumably that would degrade the performance of whatever, looking at things or right, so it would be even if this was more favorable, that if you got like reducing the digits really made it much less accurate from a attack point of view, it would not be very desirable from the manufacturer, the user's point of view.
Right, because it would look kind of bad basically if you had very
Something, right?
yeah, or it'd be like very discrete jumps in the display.
It's tough.
But we did try to investigate, like we were confused, right? Like, okay, we reduced it a lot and how come it doesn't work that well? Like it doesn't mitigate that well. So it's actually what we think, though we didn't fully explore, is that it's related to the timing more of it. So like classifying a word not only depends on your head movements, but how long your head is moving for. So like longer words and even for like words that are the same length in terms of number of letters, it takes some people longer or shorter. So that seemed to be a very key signal rather than like exactly how they're moving their heads.
So is it possible to determine the like key combination, for example, Control+C or Control+V or something like that on the key?
Yeah, we did some of that. Maybe I think I skipped it, but this is the character pair classification. So we didn't do control, but we did like English letters. It's not like great. So like, here's our best approach, right? Top 5 accuracy is 70%, but the top 1 accuracy is only 30%. So it's not like that good because it's really hard to classify 2 characters. But we think like if that at least gives you some information. So if you were to feed that into like a password cracker, you've at least reduced the search space like a lot, even if the accuracy is like not like amazing. It's not like 93.5 or whatever in a machine in like object detection or something, right? Cool. So this is one set of work. Oops. Got stuck. What?
Hard content.
Huh? Oh, see you, Robert. Is this working? There, I think it crashed. Hold on. Let me just redo the stream. Oh. Okay. What happened? All right, so just like in lecture, let's take a 2-minute break. Coming back. Share on Zoom again. Okay. So here's where we are. So I talked about various things you can do with the headset sensors. Let's move on to the second class of attacks, which was what happens when you manipulate this shared state. And I'm gonna hide this thing. So multi-user attacks on shared world state. So how does this work? We need to have some background information. So what is this shared state? So when you have XR devices, they need to read or write to some kind of shared state to keep track of the virtual world for all users. So this is a clip from Google AR Core demos. So device 1 comes, it scans the world, and it uploads some data to the cloud and displays some virtual content here. And then device 2 comes along, they want to see the same virtual content. So it scans the world and then uploads some data, and it's able to see the same virtual content. So this cloud is holding the shared state. And the question that we asked in this work is, what happens if an attacker poisons the shared state? So what's our threat model? We're going to repeat this picture. I have two users now. One user is a regular user with their sensors, SDKs, and applications. And the other user is a malicious user who's participating in the same session. So the attacker uses an unmodified AR application to access the shared state. They just pretend to be a regular user with no special permissions. So let me tell you more about this shared state. So a shared state is a set of information that enables the consistent experience of all the users. So in particular in AR, the shared state contains a point cloud in the environment and also whatever holograms you want to display. The point cloud is constructed from your camera. As you move around, you sense the environment, it constructs these point clouds and sticks them there. And the main way we think of this is accessing the shared state is like a bunch of read-write operations. Like think of it like a database. So I have keys and values. These keys are information about the real world. For example, a point cloud I constructed, or sensor information from the IMU or the GPS data. And the value that I get back is a hologram. And we find examples of this in many existing AR SDKs. Like here's Google AR Core. It has host and resolve, which are basically like read and write APIs. So let's see an example. So here's my AR shared state, and it's storing the point cloud in the hologram. And Alice wants to go read. And she's going to send a key. The key is some information about the real world that she sensed. She uses this key to access the shared state. And that unlocks it and gives you back the hologram she wants to see. And then on the other side, maybe Bob wants to write. So Bob also accesses the shared state with a key, which is some information about the real world, writes to it, unlocks it, and maybe updates the hologram from the Pikachu to the sign. So this is the way we think about shared state. And what we did is we looked at a bunch of scenarios that exist in reality today. So we created a taxonomy of these shared states, local versus global and curated versus non-curated. I'm going to skip the details, but I just want to say that we found real world examples in each of these categories in the taxonomy. So the three categories are scenario A. This is Google AR Core. It uses Google's Cloud Anchor API, and attackers can read and write to the shared state. We also found another one, which is global curated. Oh, they're swapped. OK, my bad. But anyway, the three versions are the scenario B, which is here, and scenario C, which is here. So these two are Google APIs. This is Cloud Anchor API. This is the Geospatial API. And the last one here is Mapillary, which is like an open source mapping company. And it's owned by Meta. It collects a bunch of information about, it's kind of like Google Street View, but open source. Oh, not open source, crowdsourced. It's basically like a crowdsourced Street View. So these are three examples of shared state that we find that can drive AR applications, and they all have APIs that you can access to read or write to them with varying permission levels. So we demonstrated attacks on these three frameworks. So I'll show one example. This is a remote read attack. So here the attacker has control of her own device. And under normal operations, she would show regular inputs to her camera and then be able to retrieve the holograms. So here the hologram is this little like 3D axis. And then what happens in the attack scenario is that I can show a fake key or like adversarial image basically to the camera. And in this case, what happens is that using this fake key, we're able to retrieve the value, which is again this 3D hologram. So here in this example, the fake key is basically a photograph of the real world location. So you can also think of this as basically an image spoofing attack. Instead of the device being physically present at that real location, I'm just going to show it a photo of that location and it still works. So you might think, well, maybe this is trivial. Like, why would I want to do this? So this information is not very interesting, but you can imagine some scenario. Maybe I went to the chair's office and I saw some private information there, and I'm not supposed to access it later when I'm outside, but I just took a photo, I showed the device a photo, and I accessed that private information again. So that's an example. And we did this across a bunch of environments, so office, home, and outdoor environments. We used a bunch of Android phones, and we showed good success across various types of scenes. This is the success rate in when the scene doesn't change, and this is the success rate when we add a bunch of random stuff to the scene, basically making the scene dynamic. So let's say we basically made it work half the time, right? It doesn't always perfectly work. The main difficulty is like when you have your device and you're showing it a photo, the device also uses depth information and your photo has no depth. So you kind of have to like fiddle with it a bunch, and sometimes it works and sometimes it doesn't. And the other key thing is the device has to have the right orientation. So if you do it at the wrong orientation, like you do portrait mode versus landscape, it also may not work. So that's why the attack is not perfect, but we still think the success rate is pretty decent. And this is just more like environment variation. Maybe skip ahead. Okay, and then the other scenario I want to show is like a poison right. So what this looks like is we play with Mapillary, and we want to do a poison right to the shared states point cloud. So for this one, we worked with Mapillary. They're really nice to us. They have these community outreach people. So we basically, how do we get through to them? We had this grant from Meta to look at like trustworthy AR, VR, and we were telling them all of our ideas, and they were like, well, why don't you talk to these Mapillary people? And then we reached out to Mapillary, and they were very nice to us. And we were like, we have this idea, can we try it? And they're like, yeah, okay, here, we'll give you a little sandbox. So that way you can play with it on campus, and your sandbox won't affect like public users. So that was really nice of them, and that basically enabled us to do these attacks without affecting any public users or having any ethical issues. So what did we do? We basically went around campus, and we collected a bunch of data. And before we uploaded it to the shared state, we basically messed around with the metadata. So we swapped some of the GPS coordinates and also manipulated the images to like add fake things to it. And we upload it there, and we basically see, does the Mapillary pipeline allow you to ingest it? And it turns out they do, as long as you do it in a certain clever way. So once you've written that poison data to the shared state, then a victim who later comes and reads it, will see like the wrong information. So what does it look like? So let's say in the upper row here is the desired one, which is normal. So it's looks kind of clunky, but here's a grassy scene, and you want to have like a virtual annotation that says it's safe to dig here. And in the second location, you wanted to say it's dangerous. So once we upload the wrong data and we poison the shared state, a victim user who comes across will then see the wrong signs at the wrong place. So they'll say it's safe to dig here and unsafe to dig in this grassy field. So that's basically the implication of this attack. Yeah. We also explored defenses for this. So because it's basically image spoofing, this is some ongoing work where we tried to figure out if you could detect if you're actually looking at the real scene or an image of the scene. So we tried different things here. Basically, we tried to leverage the depth sensor to try to figure out, is it the real scene or is it a fake scene? And it works somewhat. Here's our overall accuracy in detecting if it's fake, a real image or a fake image, so a real scene or a fake image. But it did require like depth camera. And some of the devices have depth cameras and some of the cameras don't. Some of the devices don't. So we're not really sure if it'll work on all AR devices in the future. So I basically told you about two kinds of security problems that we study. The main idea is like you sense a lot of information about the shared world, and that information is being shared between applications or between different users, and that exposes new weaknesses. So I showed you the typing one, the basically system attacks from the malicious applications, and I showed some multi-user stuff as well across different users from the shared world state. And what we found so far is that these early mitigations, easy mitigation strategies were not very effective. Cool. So any questions about this so far? The shared state stuff? Personally, I think the shared world state is like kind of an interesting aspect. Like if we go to more of these more collaborative applications, I think we'll see more and more issues there. And I know people are researching.
Or the fake image poisoning, like the weakness to like you have like can you use like directly use some fake image detector to detect rather than like including more sensors? Because I think like because if they want to poison an image, they need to do some edit to the original image, like photoshopping. Can you just directly use this kind of image editing detectors?
Yeah, so like when we first tried to manipulate the images, and if we did something very like obvious, like if we had a picture and we just put in like a stop sign, the mapillary would reject it because I think it might maybe has some detection already. So when we did it, we have to be a little more clever. Like we had to put the stop sign in at the right size and the right location. And the other difficulty is you have a sequence of images. So you have to make sure whatever poisoning you do to one image like affects the later images in a realistic way.
Really realistic.
We think that the mapillary pipeline, yeah, already does some stuff like that to like detect if you're putting in fake staining. So it didn't work at first. We had to like do some stuff. Yeah. Question? Yeah.
And the first weakness, I think you mentioned something about differential privacy guarantees. Is there an example for it? Like, is it like mess around the order of the keyboards or something that could provide DP guarantees?
Yeah, so some people are working, I can send you a paper later. Some people work on taking those sensor values and like adding noise to it to provide some differential privacy guarantees. So I think that's a really cool line of work as well. And it turns out how you add the noise depends on like the kind of XR data you're trying to protect. So if I'm like trying to protect the height of a user, they might add noise in one way. And if I'm trying to protect like the arm length of a user, they have to do it in a different way. So it's cool. Like people do study this. Yeah, the differential privacy stuff. Yeah.
You mentioned that some of the systems don't have a depth sensor, but I would just guess that these days with deep networks, you can do pretty good depth estimation even from a single image.
Yeah, yeah.
Maybe, oh, that looks like a flat, whatever, so it's probably not real. I'm just guessing, I don't really work.
Yeah. Well, I guess they already do a little bit of depth sensing, just even if you don't have a depth sensor, because you're capturing the scene from multiple angles, they use that already.
Stereo.
Yeah, but it's not like perfect. Yeah. But, and I know there's like people who work on estimating depth from images and stuff, but I don't know if those have actually made it onto these devices yet. But I think they must, right? But at least for image editing, right? I think I've seen some cool examples from the cameras and things, but I don't know if they're in like the AR frameworks. But yeah. But yeah, maybe that'll make our life easier if we can do really good depth sensing.
I have a question about the first weakness because as far as we know, so many the permission to many sensors, they are blocked to, like background applications. For example, you cannot access microphone from the background in iOS. So why is this, like the sensors the data are still open to all these background applications in the first?
Yeah. So the reason is because some of the information you just can't block. So if I block the head pose information, then the background app will basically be frozen. So, and that'll be uncomfortable for the users.
I believe it's a common practice. So to block the permission of, like body sensors to background apps.
Yeah, but what we found is like the head pose is often not blocked because it's so crucial. But actually over time, we found things have changed. So when we first did this work, it was very easy to access. But later we found that in more recent devices, we had to do students had to do some hacking to figure out how to get those data, but it's still obtainable. Yeah, we had to use some old APIs basically. But as far as we've seen, like the performance counters and stuff most of them are still there, the ones that we used. Yeah. But yeah, you're right. Like there are global permissions, like voice and stuff is pretty controlled. And I think sometimes the hand gestures also.
It's like Google Apple, they are, like tightening the permission.
Yeah, yeah, yeah. Cool. So I guess the last work I'll just present really briefly because I think, yeah, I'll just present it very briefly. So just going back to this picture. So we talked about the security stuff on the sensors and the shared state, and I want to provide a little bit about opportunities we have. And this is more on the line of mobile streaming. So it's less on the security aspect, it's more on multimedia systems and networking. So the main idea is, can we stream user 3D content in an efficient way while leveraging our understanding of how XR users behave. So I only have two or three, maybe 3 or 4 slides on this. So the main idea is 3D content is getting heavier and heavier. So we can deal with traditional representations like mesh representations. Over time, we're going from simple mesh representations to more and more complex representations. And we also have new representations like 3D Gaussian splats. So 3D Gaussian splats represent 3D content as a bunch of 3D Gaussians, which you can think of as a generalization of point clouds. So the challenge is the content is getting bigger and bigger, and we want to deliver it efficiently to the headsets. But we also see some opportunities by leveraging human behavior as they navigate the virtual worlds. So we can think about small-scale user movements, like users navigating around a single 3D scene. This is a scene from a Gaussian splat scene, users just looking at a bicycle from a weird angle. And we can also think about large-scale user movements. So there's this concept of world-scale AR, where many Pokemons are placed at different places in the world, and the user moves around large scale. So the main idea we have is that if we can predict what the user will do, we can provision better resources for their delivery. The general scenario we think of is there's some content that's stored in a server, and there's a client that wants to retrieve that content. And I can try to retrieve that content at the appropriate times and then display it to the user. That's the basic setup, right? So remote and local. So what is our secret sauce? How are we going to improve this? Well, the main idea is, can we use some user behavior prediction based on how users interact with the XR content? And also, can we introduce different quality levels or layered representations of 3D content? So combining these two aspects, we can do a better job, presumably, than just regular 3D content. So as a quick example, here is some data we collected from Pokemon Go. We want to predict what things that users are likely to look at next. So you ever played Pokemon Go? This is the screen that you see, and users walk around. And this is the real world environment. So users can walk around in the real environment and also in the virtual environment. So we collected data from this. We collected data from a bunch of users playing Pokemon Go across different zones, several states. In the end, we collected almost 300 minutes of users playing Pokemon Go and their mobility traces. So the main idea is then, can we use this data to drive scheduling algorithm designs and make good decisions? So I'm skipping, I guess, all the details, but here's some results from our recent work. So what you'll see here is a user looking at virtual content, and there'll be 4 videos playing. This one will be if I just pre-downloaded everything in advance. These are 2 baselines. And this was our approach that we proposed that does all the user prediction and intelligent scheduling in the background. So I'm going to play the video. So what you see is that ours has more quality coming up, and the baselines are not retrieving the content in time. This one eventually came up, right? So let me replay it from the beginning, because most of the difference is at the beginning, because as time goes to infinity, everything all becomes the same. But you'll see again from the start from the start, ours is basically better. Right. So I skipped a lot of details. There's much more behind this hard work of the students. But the main idea in these streaming works is the 3D content is getting larger and larger. I don't want to pre-cache everything. I can optimize what content to get when, driven by user traces and efficient representations we have of the data. And then using that, we do things on prototyping with Android devices, with VR headsets, and we try to show like good visual quality and it's downloaded quickly. Great. Maybe I'll just mention one more idea that I have, right? This is not a finished work, but it's just something I'm interested in. The reason I'm bringing it up is because this is a topic I want to work on. So if there are people who are interested in XR or distributed systems, I want to talk to you. So this is just some ideas I had about how you have multiple users available. They are all interacting with each other and interacting with a shared state. So can we think of this as a distributed system? So multiple users reading and writing to the same thing. We need to ensure consistency, how they update the data in a reasonable way. This is the vision. So a specific example of that is Alice and Bob. And suppose they both try to manipulate the virtual content at the same time. But you see they move the virtual content in different ways, right? Oops. Play it again. So there are two users, they move the virtual content in conflicting ways. So how do we resolve that? We look at current consistency mechanisms that existing platforms use. They basically find that they're inefficient. So I'm interested in using more mathematical tools from sort of distributed systems or formal methods to try to model the systems and provide guarantees. So here are some initial experiments that we had. What you'll see is different methods of ensuring consistency. So there are going to be 3 phones. Each phone is going to, in each session, one of the phones is going to update the virtual character. And those updates should be propagated to the other phones. And then this is our method. This is going to be a baseline method. And this is going to be another baseline method. So I'm going to start the video. And what you'll see is these little Android characters moving around. And ideally, you want all the Android characters to move together. Okay, so let's play. Try this. Oh, sorry. Did they play? Let's see. Okay, yeah, they're trying to play. So it's kind of hard to see because there's small movements, but you'll see like this one is stuck, right? It's not really working well. This is our approach. They're mostly in sync. And this one, it's pretty good, but it sometimes has some sync issues. So that's the kind of problem I'm interested in, but this is just a specific example with like moving little virtual toys objects around. And I want to explore it more. Maybe there are people who are interested in this and want to think about it with me. So basically that's it. I want to conclude here. So I'm going to repeat the picture again. We discussed weaknesses at the headset sensor side in the shared world state and ways of exploiting user behavior to improve efficiency. Trying to modulate between the real world and the virtual world introduces these kind of weaknesses and opportunities. So I guess there I'll conclude and let you guys out 5 minutes early. I'm sure everyone wants to get out. Well, it's only 4:30, so that's it. Thank you. So we already had questions. If there are more, I'm around. Otherwise, yeah. Cool. Thanks, Chi. Thanks, everyone.